welcome back to this class on design for biosecurity. So, previous class we were talking about the patch clamp technique, and I shared my understanding about current clamp and the voltage clamp. So, if we just do a recap, when we talk about the current clamp, we are talking about you are fixing the current and you are measuring the voltage, which is exactly the case of when you are measuring the action potentials, versus when we are talking about a voltage clamp, when you are clamping the voltage and you are measuring the current. And I told you how we could clamp the voltage. So, say for example, this is a cell and you have to clamp the voltage across it. So, inside we know it is negative, outside we know it is positive, and imagine this is a battery and you have some way or other to control the voltage across this, okay, across this cell. So, depending on how you are changing the voltage, the ion channels opening and closing will be dictated. So, in another word, you are artificially creating a situation of controlling the voltage across the cell. In other word, controlling the voltage across the cell, and in a stepwise manner you can vary the voltage. So, we know the resting membrane potential is approximately say -70 to -80 millivolt. Okay. Now, from -70 to -80 millivolt, you could create a protocol of say increment of 10 volts. So, if this is -70 millivolt, you can go to 60, 50, 40, 30, 20, 10, 0, and likewise you can go further. Now, the time of the pulse you decide. So, this axis is basically the time, how longer will be the pulse, and this kind of decision making is empirically driven. People after several years of experience pass on the knowledge, and mostly this is how it works. But of course, you always have the liberty to change. You could have a smaller pulse, you could have a bigger pulse. This is when I say smaller or a bigger pulse, I am not talking about the increment, I am rather talking about the time, how long you want to give the pulse. Okay. And then there are people who change the shape of the pulse. They can give it like this, they can give it like this. There are hundreds and thousands of things you can do in this situation, right? And based on that, what you are measuring is that your I here is unknown. So, you are measuring the current. So, essentially if you recollect when I told you, so you get something like this, you get an inward sodium current followed by outward potassium current, right. So, this inward sodium current is a function of the opening of the ion channel somewhere in this zone, and this potassium current open out here, right. So, in other words, what you are monitoring is the influx and efflux of sodium and potassium ion. Similarly, you can do that for calcium also, but it is a little tricky, but you can do that, right. Now, say for example, you have a bioterrorist agent like TTX, which is tetrodotoxin coming from the pufferfish. So, what tetrodotoxin does, it goes and block these sodium channels. So, in other words, when you are doing a voltage clamp, what you will observe is that you won't observe any more these currents, which are the sodium currents, they all will be missing. What you will see instead is only this current. So, in a way, you can isolate one current from another current. So, in other words, you can influence the efflux and influx by using the toxins. Similarly, say for example, you use 4-AP aminopyridine. This is a thing where you will see this particular current is going off, right. Similarly, because it is a blocker of the potassium flux. So, in other words, it is blocking the potassium channel. Similarly, if you use something like curare, this is another toxin which is used in the Amazon basin. So, what curare does, in the next slide we will talk about it. What curare does is, we know we have the motor function connecting to our muscle. So, these are the motor neuron coming from our spinal cord, and here you have the muscle. Okay. Now, this is where it forms what is being called as neuromuscular junction. In short, many a times they call it NMJ. This particular spot is extremely important from multiple perspectives. If we want a drug or a toxin to induce paralysis, this is exactly the zone you may target. And since olden days, when humankind was all into hunting animals, they developed a series of toxins from multiple sources, from the plants, from the fungus, from snake venom. All these toxins, mostly when we are talking about paralyzing animal, they go and act at neuromuscular junction. How they do so is very interesting. Is what, first of all, you have to understand what is happening at the neuromuscular junction. At the neuromuscular junction, action potential travels out all the way out here. Once action potential travels at the muscle, step 1 was electrical signal reaching the neuromuscular junction. Step 2 leads to secretion of neurotransmitters from neuron, and these neurotransmitters are supposed to bind to muscle surface, and there they will do two things. One, they will initiate an electrical signal, and parallelly this electrical signal will initiate a mechanical motion. And this whole orchestra of first an electrical signal transforming into a chemical signal, then again invoke an electrical signal, and this electrical signal leading to a mechanical signal. It is a well orchestrated process. Now, only way you can disrupt the process chemically is if you disrupt some of the chemicals. So, one of the things what curare does is, once you insert curare here, say for example, close to this proximity, curare goes and binds to the site where neurotransmitters are supposed to bind to the muscle. In other words, this is the zone where these neurotransmitters are supposed to bind. Curare goes and binds there. And when curare binds there, so automatically the cations cannot enter, because most of these neurotransmitters at the neuromuscular junction, most of them are acetylcholine. This neurotransmitter goes and binds out here onto the muscle. So, it is secreted from here and it goes and binds to the muscle. So, if we redraw this, it will look something like this. If this is the end of the neuron and if this is the muscle surface, we are looking forward to at the microscopic level. So, here the neurotransmitters are being released. These neurotransmitters comes and bind to these pockets, which are neurotransmitter binding sites. So, in other words, in this situation, these are acetylcholine binding site. Okay. Now, they will bind here. As soon as they bind here, they will open up cation channels. Those cation channel opening will lead to the influx of sodium here from outside. As you have already observed this in action potential, there will be an influx of sodium. This influx of sodium will lead to a generation of an action potential. This action potential in the muscle will lead to another cascade of events, whereby within the muscle there is actin myosin filaments. There will be a contraction which will happen, which eventually is the what we know for the muscle as the mechanical motion of the muscle. So, in other words, this orchestra happens in the presence of calcium. So, there is a calcium spiking. So, there is a calcium current, there is a sodium current involved in it, and then there is a potassium current involved in it, and then there is a sodium potassium ATPase pump. So, at every level you can block this transmission chemically. So, the first what we are talking about when curare comes into play. What curare does, curare goes and binds to these sites. Once they bind to this site, this action potential will not be generated, right, because there is no influx of sodium which is happening into the system. There is another way you can do. Say for example, this happens, but then you have calcium blockers into the system. So, they will block the mechanical motion, because those calcium blocker can bind to the another organ within this part, which is called sarcoplasmic reticulum. In short, they call it SR, and it has two calcium channels. One is called ryanodine receptor RYR, and other one is called DHPR receptor, dihydropyridine receptors. Now, both these DHPR and ryanodine receptor works in cascade. They secrete calcium momentarily and pull it back. Okay. Of course, for pulling it back, there are other pumps which are involved in the sarcoplasmic reticulum. So, what inside what happens if this is the SR sitting here, this SR gives away. So, what is happening here is what I draw just prior to this, I am redrawing it. So, when the curare binds here, I told you what is happening. Now, I am talking about what is happening with the sarcoplasmic reticulum. Sarcoplasmic reticulum is an interesting organ. It efflux or calcium comes out from it and it pulls back the calcium by using its pumps. And in order for it to secrete the calcium, there are two players I talked about, DHPR and RYR, ryanodine receptors. Okay. Now, this transient increase and fall of calcium is something like this. This is called a calcium current. And the reason why calcium has to be regulated is calcium can be excitotoxic. It could be toxic to the cell. So, it has to be removed very fast. So, if you use DHPR or ryanodine receptor blockers or a toxin, then you can stop this process. In that process, what will happen? The mechanical activity of the muscle will be compromised. Okay. So, this is the other way you can monitor this or control this event. There is a third way you can control the event. Say for example, you use sodium, potassium, ATPase pump blocker. That is the third way you can do it. So, if you look at it from a generic perspective, there are multiple ways how you can block these events. So, say for example, let us summarize, you can use TTX, tetrodotoxin. It will block the sodium channels. If it blocks the sodium channel, so automatically there will not be any further generation of sodium current. If there will not be any generation of sodium current, so the action potential what we know will be cancelled out. If the action potential is cancelled out, this action potential which triggers the SR or sarcoplasmic reticulum to secrete the calcium or the spiking of the calcium, that will be, if that is compromised, it will compromise the mechanical activity. Same things happen in curare. When curare is getting into the game, curare is blocking the acetylcholine binding sites and thereby stopping the action potential generation and rest of the event. Simultaneously, you can think of about the toxins which will block the sodium potassium ATPase pump. So, that must give you an idea how sensitive human body is and how many different ways you can create problem to the system. And most of these agents, whether we are talking about curare, whether we are talking about TTX, whether we are talking about 4-AP, these are all regulated compounds. These you cannot openly go and buy them in the market, because under the federal laws of different countries, these are restricted compounds and they are all considered as biowarfare agents. So, possession of these kind of compounds is just like in India you want to carry a gun. In order to carry a gun, you need to have a permit, you need to have a license. Without that, you cannot carry a gun, right? Similarly, if you want to have curare or TTX or any of these compounds, you need to have a permission from concerned authorities, otherwise you cannot carry these kind of compounds, and this list is huge. And in the next class, we will come about some of the techniques by which these are being understood. So, I will close in the class. In the next class, we will talk a little bit about how you can use this neuromuscular junction as a sensor before we move on to the extracellular recordings and the field effect transistors. Thank you.